We will begin our journey by looking at the kinetic theory of gases, at least a simple version of it. This will help us gain some intuition. The reason we will look at gases is because they're actually the simplest kind of matter, at least when they are in equilibrium and still. When you think of a gas at equilibrium like a continuum, there is not really much to describe. However, when you accept the reality of atoms, the picture becomes immensely more complicated. The amount of atoms in your room is bigger than the number of stars in the universe, and the amount of information that will be needed to describe their positions and velocities will be greater than 1,000 times the information on the whole internet. One can see why the classically minded people of the 19th century will find this horrendous, but we now know better, and we still accept nature as it has revealed herself. There is another more fundamental reason, apart from the sheer number of particles, that prevents us from having a deterministic description of all the particles of a gas. A reason that will actually prevent a deterministic description of a single particle in the gas. Basically, it's an example of the butterfly effect, which mathematically comes as an exponential amplification of error. The consequence will be that if we wanted to describe the trajectory of even a single particle in the gas, we'll need to know precisely the position of everything else in the universe. A kind of microastrology, I guess. Let us see why. To do this, we're going to consider this setup I've prepared here, which is composed of these three balls, which are supposed to represent, say, air atoms in your room, for instance. And just for simplicity, we're gonna take the three yellow atoms to be stationary, while only the red atom will be moving. We have set up its velocity in such a way that it goes basically in that direction and bounces on the stationary atoms, and it sets off in that direction. So yeah, just do remember the fact that it leaves in that direction, because that's gonna be important for what we're gonna see now. Because now we're gonna imagine that there is some object very far away, like in another galaxy or something, that we haven't really taken into account. So let me just go there. This funny looking object over here, it doesn't really matter what it is, but it's very far. However, no matter how far it is, it will have some gravitational effect in our system. No matter how weak, it will have some. So if we come back to our system over here, we can assume that in this case, for instance, the presence of that object actually causes the velocity of our red atom to be just slightly different, just like 1% in whatever units this thing uses. And we can just see what happens if we let it run on its own. We can see that at the beginning it looks pretty similar, but you can see that the end result, actually the ball goes in a completely different direction. And just so that you don't think that I'm cheating you by choosing a very special position, I'm gonna just move this around a little bit. Let's see what it does. I don't know. Okay, so it goes that way. Well, you see, it does go in a completely different direction. I mean, it could happen to go in the same direction in the two cases. The point is that no matter how small the deviation in the initial velocity is, that is, our uncertainty in it, after enough collisions, that uncertainty will propagate more and more up to the point that we won't be able to predict where the velocity is going. I mean, to be able to predict where it will be going, we will have to know about the exact position of everything in the universe that could have any influence on the velocity of the particle, no matter how small that effect is. But we can not only just see this, we can actually understand it a little bit better if we enter the world of geometry. Okay, so I opened up Geogebra and I'm going to make a 2D representation from above of the situation we have just seen, only involving two balls. Okay, so I cleaned up the scene a little bit and added some nice colors and stuff so that we can see what's happening a little bit more clearly. This scene is a bit of a simplification, but anyway, what these lines represent are the trajectory that the ball will follow if it started with the deviated velocity. So that means that if the ball has the velocity which doesn't have any deviation, it will just follow by assumption and for simplicity this straight path along the x-axis will bounce back along. On the other hand, if the ball has a deviated velocity by a small angle, it will follow this red trajectory like this and bounce like that. Now, the directions in which the ball bounces back we can represent by two vectors. So this is the direction in which it bounces when it has no deviation. This is the direction in which it bounces when it has the deviation velocity we consider. Now, what we want to calculate is how much the uncertainty in the velocity has increased. That is, the initial uncertainty can be represented as this angle, delta theta 1, and the uncertainty after colliding can be found by drawing this line and then finding that angle, which is the same as the angle between the vectors u and v, which represents the uncertainty in our velocity after the collision, given that our uncertainty in the velocity to begin with was whatever it was. So we want to find a relation between these two angles to see how much the angle increases by at every collision. To do that, we'll first note the following curious fact. If we look at the distance between the edge of the circle and the point J, as we decrease the initial angle, our initial uncertainty and velocity, we see that that distance actually converges to some value. In this case happens to be 1.55. It's not hard to see that this value will be some fraction of the radius. In fact, we can try to change the radius. We can see that the distance m seems to just scale with the radius. I don't think it's trivial to show exactly what the relation between this distance m and the radius is. I think for the case in which the ball is initially at infinity, I have an argument to show that that distance will be half the radius. But in the general case, I don't think, well, I leave it as an exercise for you. But let us assume that m is indeed proportional to r, which we can write here as an assumption. Let us just call this vertical distance over here delta x. Then, if the angles that we're considering are small enough, then we can use the small angle formula and approximate both delta theta 1, that little angle which is almost invisible now, and delta theta 2 by their tangent. That is, we can approximate delta theta 2 by delta x over m, but using this relation where m is proportional approximately at least to r, we can just find that delta theta 2 should go like delta x over r, a dimensionless ratio. Again, using the small angle formula for delta theta 1, we get the following formula, where L is this distance. Finally, combining the equation for delta theta 2 and delta theta 1, we can get that delta theta 2 is delta theta 1, and by rearranging this equation, we get that delta x is delta theta 1 times L, which if we substitute in here, we will get this. So our conclusion is that within some approximations we have made, but which shouldn't really change the result that drastically, the uncertainty in the direction is multiplied at each collision by the ratio L over R, where L is the distance between collisions. In this case, because this is the initial collision, is the distance between the starting point and the next collision, but for the next collision it will be the distance between collisions, the ratio between that quantity L and the radius of the spheres. So I'm just rewriting the equation we just got. I've dropped the delta from the names we gave to the angles and I'm using an equal sign because my program just works better with them. Of course, we will have a similar equation for the uncertainty after the second collision, which I call θ3. Again, just using a trick for my program, which by the way there is a link for in the description. We substitute θ2 in the equation for θ3 and we get that. You can see that this pattern will continue, so that after each collision we multiply by L/R, so after n collisions, actually it should be n-1, but anyway, we get L/R to the power of n. The initial angle we can write using the small angle formula like we did before, where delta x is the deviation by the faraway object. Now, we want to find how many collisions are needed, that is n, until the uncertainty in the final angle is very big, say of order pi in radians. Now, let me just rearrange. And apply this identity for logs. So, we finally get an equation for the number of collisions needed so that we are totally uncertain of the direction in which the ball travels in terms of the initial deviation. We can write the initial deviation using some basic mechanics and the law of gravitation, like this, where m is the mass and L is the distance to the faraway object. Delta t is the time until collision, which I can write in terms of the particle's velocity. So we can take this to Wolfram Alpha and plug in typical values for all these quantities. I'm also going to assume that the faraway object is an electron, which is found at the edge of the observable universe, just to show how ridiculous is the sensitivity of the particles in a gas. We find that we only need 53 collisions, which we can estimate takes only a few nanoseconds in a typical gas. Just think about that. Even if you knew perfectly well the positions and velocities of a gas now, a few nanoseconds later, you wouldn't be able to predict where it'd be, even if all you missed in your picture of the universe was a single electron at the edge of the universe. All this obliterates the possibility of a deterministic description of a gas. Instead, we must embrace uncertainty. There is a plus to this though, that is that it will simplify our description greatly. I mean, when we get to thermodynamics, we'll be able to describe an ideal gas with just 3 numbers.